So keep in mind that I'm going to look at how to find critical numbers or critical points, and then classify the critical point using these three properties. The critical point is the critical point symptotically stable, unstable, or semi-stable. Okay. So let's move on to example 4, where we're going to have. So for this example, it's autonomous system, right? But later on, we will have a non-autonomous system. So the idea is to sketch the direction field in the phase plane for the system. The xdt equals to negative x, dy dt equals to negative y, 2y, and define the critical point before you can analyze the phase plane. And then later on, after this phase plane, you can actually classify the critical points to be asymptotically stable, unstable, or semi-stable. Okay, so first, to determine the critical point of the system, we set each equations to equal to 0, right? That's what we see earlier, the concept or the theory that to find the critical number, so the critical point is that the derivative equal to 0. So that dx dt equal to 0 and dy dt equal to 0. In other words, you just set this equal to 0. And you see that x is equal to 0 and y is equal to 0, so therefore that is the critical point on the plane. Then the critical point is 0, 0. So the next thing that you need to determine is to determine something called Nullclines. So this Nullcline is very similar to the asymptotes that you learn in calculus. All right, so Nullclines. For us, there are two Nullclines, the x Nullclines and the y Nullclines. So for x Nullcline, this is where x prime equal to 0. So you set this equal to 0, right? Or you see that negative x equal to 0 or x is equal to 0. When x is equal to 0, that is the y-axis, the entire y-axis. And the second nullcline is y nullcline. And y prime equal to 0 or negative 2y equal to 0 or y is equal to 0. So this is the x-axis. So now you have enough information to do the phase plane analysis and draw out some directional field of the system. So this is x, this is y. And so x is the y nullcline, and y is the x nullcline. Now on the x nullcline, right? So the x dt is equal to negative x. So when x is positive, the x dt is negative. When the x dt is negative, that means it's pointing down, right? It's decreasing, so it's pointing down. So this is the origin. So this is the critical point, 0, 0. Doesn't matter how many arrows that you use here, you can use 1. When x is less than 0, then the x dt is positive. So therefore, it's increasing. Right? Now for the y nullcline, the y nullcline depends on this equation right here, dy dt equal to negative 2y. So when y is positive, dy dt is negative, so it's decreasing. And when it's decreasing, and when y is negative, then dy dt is positive, so it's increasing. So the x nullcline and the y nullcline indicate that everything pointing toward the critical point. Right? You can actually conclude that the critical point is a asymptotically stable point. Okay. In addition to that, from this suggestions of the nullclines, you can point out or you can graph out some direction field. Okay. So everything has to point toward the critical points. So you can conclude that from the figure, we can see that all the solutions flow into the critical points. Zero, zero. Thus, 0, 0 is symptotically stable. So to determine the critical number or critical points, we set the x dt equal to 0 and dy dt equal to 0. The critical point is 0, 0. All right, so the next part is to determine the Nullclines. Similar to the last example, the Nullcline is going to be the x-axis and the y-axis. But for the formality, I'm going to write it down here. We have x Nullcline to be that of dx dt equal to 0 or x equal to 0. So this is the y-axis. And for the y Nullclines, we have dy dt equal to 0 or y is equal to 0. So this is the x-axis. So you have the critical numbers, you have critical points, and you have the Nullclines. So you plot the phase point. So this is y, this is x, this is the origins, and also the critical numbers or critical points. So for the x Nullcline, let me note it here. So this is the y Nullcline. This is the x Nullcline. For the x Nullcline, it depends on x. So when x is positive, the activity is positive. So therefore, it's increasing. Right? So it diverges away from the origins. When x is negative, it's diverged away from the origin as well, but toward the negative side, like that. And for the y Nullcline, depends on 2y. So dy dt is equal to 2y. When y is positive, right, dy dt is positive, so it's get away from the origins, right, toward the positive side. And when y is negative, dy dt is also negative, so it's decreasing toward negative infinity. And it suggests that, right, all the point will eventually get away from, or all the solutions will get away from the origins, right? All the critical numbers or critical points. Because of this analysis, it suggests that the origin or the critical point is unstable. So from the figure, we can see that all solutions flow out of the critical points. Thus, the point 0, 0 is unstable. All right, so example 6 is still the autonomous system because on the right-hand side is only the dependent variable and there's no independent variable t. Okay, and for this, you also do the same thing. You find the critical points and also the Nullclines and then use those informations to analyze the direction field. Again, to determine the critical point, we set the x dt equal to 0 and dy dt equal to 0, we get. Right. So it's not as straightforward as the other examples to find the critical points. Right. So from here, when you set the derivative equal to 0, you obtain a system of linear equations of 5x minus 3y minus 2 equal to 0, and 4x minus 3y minus 1 equal to 0. So from here, this allows us to solve the system of linear system of two equations here to get the value of x and the value of y. Now you can use either substitution method or elimination method to solve the solutions. If you notice, if you subtract the second equation from the first equation, so 1 minus 2, you will obtain. So this is equation 1, equation 2. We do 1 minus 2 to get x minus 1 equal to 0 or x equal to 1. Right. So I'm using elimination method. Right? So I get 1 subtract 2. I get 5x minus 4x. I get x and negative 3y minus negative 3y becomes 0. And then negative 2 minus negative 1, get negative 1. Or x is equal to 1. Now I back substitute x equal to 1 into equation 1. We get that 5 times 1 minus 3y minus 2 equal to 0. And if you do the calculations correctly, it should give you 1, y equal to 1 as well. So the critical point is 1, 1. Right. So we finished with the critical point. Let's move on to finding the nullclines. So for the nullclines, you have x nullcline. That is, you set the x dt equal to 0, or 5x minus 3y minus 2 equal to 0. And you solve these equations, right? When you see this equation, you see that this looks like the equation of a line. Okay. So as a matter of fact, you have 3y equal to 5x minus 2. And if you divide it both sides for 3, you get y equal to 5 over 3 times x minus 2 over 3. So eventually I'm going to need this graph. So that's the x nullcline. The y nullclines is dy dt equal to 0, or 4x minus 3y minus 1 equal to 0, or 3y equal to 4x minus 1. And therefore y is equal to 4 over 3x minus 1 over 3. Right, so I have two linear equations, or two straight lines. And they intersect at a point, and that is the critical point. Okay, so this is the critical point 1, 1. In this example, we find that the critical point is going to be equal to 1, 1, and you have two nullclines that are not the axis. Right? There's just some straight line on the xy plane. Right? And you're going to do the same thing. You're going to graph these lines on the xy plane. So I'm going to move on to another page here. So you have, this is x. That is y. This is x. This is the origins. And you have the equilibrium point or critical point to be equal to 1, 1. And therefore, the two lines that you have solved when you find the nullcline, right here, these two lines, this two line has to go through the point 1, 1. Okay. So if you draw this, exactly the same as you usually do, then the two lines kind of very almost stay on top of one another. So it's really hard to see. Okay. So what I'm doing is I'm gonna just roughly draw the two lines. Right? So I have the point 1, 1 somewhere here. I just assume this is the point 1, 1. And one line is for the x nullcline. Okay. And so this one is the x nullcline. So x prime is equal to 0. And one line is the y nullcline. Y prime equal to 0. And again, if you actually plot all the details correctly, the two lines are not going to look like this. Right? They tend to look more or less like this. And it's harder for me to analyze, to actually write it out, the information. So that's the reason a little bit hesitations on my part last time, because I'm not sure if I want to follow the exact graph, or I just want to make up something to make the explanation work better. So when x prime equal to 0, that's the x nullcline, y prime equal to 0 is the y nullcline. Now you're going to manage, or you're going to do the analysis exactly the same as we did last time, but now the point of consideration is no longer 0, 0, no longer the origin, but the point 1, 1. So when you do the analysis, that when x is greater than 1, when y is greater than 1, or when x is less than 1, y less than 1, or x greater than 1, y less than 1, and x less than 1 and y is greater than 1, something like that. When you have this part, right, so x and y greater than 1, you will see that the flow is going to get away from the point 1, 1 on the positive side. So it looks like this. Or in other words, it's flow to the right. Right? Now, when the lines get below the point 1, 1, the flows go to the left. Now that's the x nullcline. Now for the y nullcline, going to do the same thing, right? When it's above the line, this line, or actually this part of the line, the flow is going up, kind of sliding in the positive direction. And below that, so that is the flow. So as you can see, the flow is kind of moving away from the equilibrium point. So you can classify that this point is the unstable point on the figure. We observe that the fluid flowed away from the equilibrium point 1, 1. Thus 1, 1 is an unstable point.